Alright, so how do we find an absolute maximum? We've done these types of problems in the past, not with the same scenario, but we want to find an absolute maximum. What do we generally do? Well, derivative changes from positive to negative gives us a local maximum, right? We don't necessarily know if that's absolute just yet. How do we, let's rewind, how do we find local minimums and maximums? Critical values, right? We need to figure out where the critical values are, where the derivative is 0. And we can figure out local mins and local maxes from that, but then to be an absolute maximum, what else do we have to take into account? Endpoints, right? Endpoints could be absolute maximums. So we need to keep that in mind and take that into account. So let's kind of review that. First thing we need to figure out are critical values. So where's the critical values? Right, where the derivative is 0. Let's look at our graph. Derivative is 0, negative 2, 2, 4.5. All right, so negative 2, 2, and 4.5. All right, so those are our critical values. We could potentially have an absolute maximum at any 3 of these points, or the endpoints, negative 7 and 5. All right, so we have to take that into account. We want to keep those in mind. Well, in other problems, how would we figure this out now? After we found those critical values, don't worry about this graph. Just like easier problems in the past, what did we do? Well, we didn't even have to do a number line for absolute max. We took the critical values and the actual endpoints, plugged them into the original function, right? Right? To figure out what's the highest, in this case, what's the highest y value that we get out. So we take them and plug them into the original function. We don't have an original function to plug this into. That's where the stuff we did earlier comes into play. We need to figure out what's g of negative 2, g of 2, g of 4.5, g of negative 7, g of 5. We need to figure out all of those things and see what's the biggest one. Well, to do that, there's got to be a shortcut, but not that much. All right. Well, we can kind of narrow some things down. So we could use the number line to kind of figure out, all right, which ones are local maximums, local minimums. So at negative 2, we go from a negative derivative to a positive derivative, right? Because it's above the axis. Negative derivative, like, so this would be a minimum at negative 2, right? So we can kind of count that out. That's not going to be an absolute maximum, right? Because that's a local min. How about at x equals 2? It's positive and then positive again. Is that going to be a minimum or a maximum? No, it's neither, right? And then 4.5, we have a positive derivative because the graph of the derivative is positive, and then negative. So if it's changing from positive to negative, that's a local max. So now really we only have to check this one, and this one.
What if it's like x equals 2?
Neither. It's neither a local min or a local max. So for this one then, we can go ahead and plug in g of negative 7, g of 4.5, and g of 5 using what we did today. So it'd be g of 0 plus the definite integral from 0 to negative 7 of our derivative. So we'd have to do it graphically.
Wait, why is 0?
So we're finding each one of these values using area under the curve and our formula from earlier. So we have g of 4.5 is going to be g of 0 plus the definite integral from 0 to 4.5 of the derivative of g of x. And the last one is going to be g of 0 plus the definite integral from 0 to 5 of the derivative of g of x dx. So let's figure out g of negative 7 first. We know that g of 0 from earlier in the problem is 5, so we can substitute that in. And instead of having 0 to -7, I'm going to switch this around and go from -7 to 0, so we have the lower value down on the bottom. And now we need to figure out this area from -7 to 0. So from -7 to -2, we just have a triangle right here. So we can find that area is 1/2 times our base is 5, height is -1. So we get an area of -5/2 for that part. And then we need to figure out the area of that quarter circle. So the area, we talked about this earlier, area of this would be, the full circle would be 4 pi, right? Pi r squared, radius of 2. But since this is a quarter circle, this area is going to be 1/4 of that, so the area is just pi. So -5/2 plus pi. So g of -7 equals 5 minus pi minus 5/2. Combine those two there, and we can combine like terms, subtract that, so we end up getting 5 plus 5/2, so that's 15/2. Sorry, minus pi. Let's get a decimal approximation so we can compare it to other ones a little bit easier. We have 7.5 pi. I'm sorry, minus pi. And we get 4.358. So that's our g of -7. Now let's figure out g of 4.5. That's going to be g of 0 again, so 5, plus the definite integral from 0 to 4.5 of the derivative. So we're finding the area right here. So we already know the area of this is going to be pi. This triangle we can figure out. Our base is 2.5, 5/2, and the height is 3. So the area here we get 15/4. G of 4.5 is going to be 5 plus pi plus 15/4. Let's just go ahead and get a decimal approximation for that. So we get 5 plus pi plus 15 divided by 4. We get 11.892. So far that's looking to be maybe like our maximum. We know there's a local maximum there. And we should kind of figure out, looking at this, that it's only going to get smaller at our endpoint, but let's go ahead and calculate that. We're trying to find out what's g of 5. Well, we have g of 0 plus that definite integral, so again, g of 0 is 5, plus the definite integral from 0 to 5 over our derivative. So area, well, we figured out the area up to 4.5. All we need to do is find this area and subtract it. Well, actually add it, but it's going to be a negative area. So this one, area is 1/2 times the base is 1/2, and the height is -1. So the area of that is -1/4. So we know these two areas and this one all combined, all of those are going to be this definite integral. So we have pi plus 15/4 minus 1/4. So we have all that and then minus 1/4. We're going to get 11.642. So So now we can tell from our three values, the two endpoints and our local maximum, that our absolute max is also our local max. So we want to explain that. G has an absolute max at 4.5, 11.892. G has a local max at x equals 4.5, and G of -7 equals 4.358, and G of 5 equals 11.642. So our local max must be the absolute max as well.